Hello, and welcome to NLP for All, our workshop where we look into the topics that helped us build large language models. Most of the workshop sessions are focused on the building blocks that ultimately help us both interface with, work with, and understand the tools that are out there for processing text. So our workshop happens on Wednesdays at 12. And first, let me just quickly share the GitHub repository for our materials. And all right, so let me just share that again. So all of our code, all of our materials will live here. I keep updating the materials as and when I find newer and more interesting tools for explaining the concepts that I'm working on. But I would say conceptually, a lot of things remain the same. Another thing that this workshop can offer is ideas for any NLP projects, any projects using LLMs of any kind that you might be interested in. So if during the talk you'd also like to ask me about any projects or any ideas that you're considering, please feel free to put it in chat. If I am unable to answer it during the workshop, I will try my best to get back to you and maybe set up we could set up a consultation or talk about the ideas more. So I hope that the space can be not just informative, but also collaborative. Today's session is an introduction to an NLP tool that's very popular and is built with the keeping memory constraints and software and hardware constraints in mind. The software is called SpaCy, and so the first step would be to find the Colab notebook where we will be doing most of today's work. If you have access to the GitHub repository, there is a link in the schedule which will link you to the notebook. And when you click on it, it should take you to the Jupyter notebook that has been saved in the repository. And there is a link on top which says open in Colab, which will open your own instance of this notebook so that you can run it on Google Collaboratory. If you can make edits to your own notebook, it will save to your account. And yeah, feel free to add to the notebook or edit it in any way that you want. It's your notebook. All right. So first up, what constitutes natural language processing? So first, it's a machine learning technology. We use it to automate the interpretation, manipulation, and comprehension of human language by computers. And currently, one of the main purposes of NLP has been for developing artificial intelligence. So at its core, the assumption that we're working with is that any condition in which a machine needs to work with natural language, if it's able to make statistically viable predictions about human language, that should be enough for most of the processes that a machine might need. Next, NLP, one of the some of the things that we are using in order to work with NLP would be we've got statistics, we have knowledge from linguistics, we have machine learning, and now, of course, there's deep neural networks, which are also integral to our work with natural language processing. Now, of course, the state-of-the-art system as far as any natural language processing, any ML AI operations is concerned is large language model work. And in which case, in order to run it, in order to train it, in order to build it, we are seeing the need for billions of lines of human generated text. So it relies on a massive text corpus. The text corpus is being used to build predictive models. And we are using all of this with massive amounts of GPU and compute time to make predictions about what text comes after a given piece of text. Now, the machines, because of the way they've been trained, because of the involvement of all of the combinations of words, phrases, and utterances and questions that the machine encounters, the sheer scale of data that we're using makes for a machine that's very good at mimicking human responses, which of course now work for both simple as well as complex queries. And the machines, of course, have our LLM landscape has evolved enough to include basic and intermediate levels of reasoning skills, and we continue to see the field grow. In this context, what would we use natural language applications for? Because the workshop is, of course, has been titled NLP for all. What is the all in the NLP? First up, we've got basic text tasks like sentiment analysis. Uh, we use it to build chatbots and virtual assistants across multiple domains. With the advent of LLMs, they're being used for things like drug discovery. We Other tasks which we've been working on for many decades would be machine translation, text summarization, things like spam detection, which is usually the simplest form of NLP or machine learning task that most students encounter. And of course, all of this culminates into some form of information extraction. And as far as where do LLMs fit in natural language processing and in the kind of direction that this workshop takes, LLMs are taking a maximalist approach. So it has been described as a sledgehammer, and sometimes our work might require more fine-tuned and targeted approach. We might not be able to have access to the kind of resources that we would need to run an LLM, or train our own LLM, or extract the data in the way that we might need it to process the data in order to feed it to an LLM. And in those contexts, knowing what the tools are which help us improve the efficiency, improve how our data works, might be a viable option. So if that's something that catches your interest, that would be the scope of today's workshop. Right. So as an example of one of the many NLP tools that are out there, I'm working with SpaCy today. SpaCy happens to be an open source library. It's been used for natural language processing for some time. It's often a part of the pipeline that goes into other trained models. It also has its own pre-trained models. It's been written specifically with memory constraints and production quality in mind. So it is good it's something that you can run on your own system without a GPU. It's something that, of course, you can run with more resources to do more work. It's really good for your first initial simple projects. And the main thing that SpaCy offers is an NLP pipeline. And the pipeline here is something that we can use to make sure that all of the tasks that are downstream can be improved by ensuring that our data quality is good. So this can be described as a Swiss Army knife approach, because there are many moving parts. There are many small and big things that you can do with SpaCy. And hopefully it's also fun. So today, some of the terminology that you might encounter is in the pipeline when we discuss the text processing is tokenization. There might be stop word and special character removal, lemmatization, and downstream NLP tasks like similarity calculations. All right. So do keep these in mind. I'll come back to all of these terms and discuss them with you. How does SpaCy work? Like, what are the steps that it takes in order to process a stream of text that you throw at it? First, the main thing that it does is while loading SpaCy, you'll be loading a specific language library. So if you're working with English, we'll be working with one of the many English libraries that SpaCy has. There are separate libraries for other languages as well. Once our language library is set up, we're going to use it in order to provide all of the tokens in our language corpus with certain tags. we're going to use these tags to parse the text. And once our text has been parsed, once it has been assigned tags, the necessary tags, we can use it for some simple NLP tasks. Now, in this case, the input can be thought of as a stream of text. And once the processing is done, the output that SpaCy provides is referred to as a document. Right? A document is nothing but the text that you provided to SpaCy, and along with all of the tags and all of the other rich language information that SpaCy will assign to it. Right? So as an initial step, in order to load SpaCy, all we have to do is import the library. In case this particular cell does not work, it might be because SpaCy has not been installed. And all you have to do is uncomment the 2 lines over here, and that should help you load SpaCy. Right? And just once you run this particular cell, it should download and install the English Core WebMD library for you, because we're working with English today, and it should import the SpaCy library. So in case you have any trouble running the installation, please let me know in chat. Now, once we have our language model downloaded, and I'll just explain the naming nomenclature here. The first 2 letters indicate the language that we're using, and the last 2 letters over here indicate the language model size. So MD for medium, there's also SM, and there's also a larger model. So depending on how complex your task is, you could decide what the size of the language model that you'll be needing today is. Right? And just as a test, for I have provided our language. I've provided a little variable here with a sentence, and the first thing I'm going to do is ask my language model to process this sentence for me, and then print the contents of the processing, which is going to be our first document of the day. So let me run this. Take a minute. All right. So I asked, my print statement was just to look into the process documents and extract the first 5 tokens that the model encounters. And that is what got printed here as a list. Now, besides the terminology that we've seen before, some SpaCy specific, or rather NLP specific terminology for us today would be first the document, which is whatever text you provide to your language model. Once the output is extracted, that would be that's referred to as the document. If you decide to slice a portion of your document, it could be 5 tokens, it could be 10 tokens. That particular chunk is called a span. It's user defined. A token is every string of characters that SpaCy identifies as, a word or some kind of meaning carrying entity. A sentence, of course, in the context of English, would be something that ends with a full stop, starts with a capital letter, and happens to carry a certain amount of cohesive meaning. And the vocab in the context of our language model is a cluster of data entries. And in this case, every entry inside our vocab has a unique hash. So it has a unique number. And every entry inside our vocab is called a lexeme. Right? So just a little document here to show all of the terms that I used here. Right? Now, let's look at how another example for our processing. Now, in this case, I've provided a longer document, and I'm asking the language model to process it for me. And after the processing, I'm asking it to print the sixth token that it encounters. And do feel free to try calling instead of the sixth token, you can call a token at any of the index numbers. See how it works for you. Next, the first task that we can look at when we're working with a language model would be tokenization, which is the first point of language processing that a model does for us. So if I want to look at, say, the first 10 tokens that the model has encountered, this is what it would look like. Next, let's if we want to call spans and sentences, SpaCy assigns tokens to longer chunks of text, which we can also call. So the first thing, if I want a list of sentences, I'm going to use the call doc.sends. So .sends would be the specific call which will look inside the list of spans that SpaCy has identified as sentences, right? And then once this is done, you can just use a simple print statement to get them out. So here I have basically a span, just as a comparison. Um, in the first example, I just asked it to print a certain number of tokens for me. And the second sentence, in the second example, I asked it to actually look inside the text and identify sentences for me, right? And in each case, the print statement can be used to verify the output. Right. So by running just this particular code chunk, we've already I conducted our first bit of NLP, which used to be quite a complex task, which is how can we programmatically recognize sentences and split up our document in order to extract meaning. And this would be a very, very lightweight way to do it without needing a massive GPU, without needing clouds, just basic language processing. Right. Next, if you want to actually access the vocabulary items, the items inside the vocab, first up, we can use the call vocab dot strings, which is going to look inside our group of words, and for any given entry, it's going to pull out the number, the unique hash that is associated with it. So the long string of numbers that you see here is the unique identifier for the token beings, right? And I can also use this long string of unique numbers in order to call the entry itself, right? So just a little backend. That's how every word is every token is disambiguated, because all of them have unique entries. Next, you can also look at all of our access tokens by type. So the first bit of categorization that we can do is we can ask our language model if a given string of characters is a word or not. And in this case, if it's alphanumeric, or if it's alphabetical, not all of the list of strings which happen to look like words will be returned. So for example, I asked my model to look at the first 15 tokens and only return the tokens which happen to satisfy the condition. This should be a word. Now, the opposite is also something that you can do. If you're interested in identifying punctuations, the call would be is punctuation. And if you like, I can give you a minute to maybe set up your own print command to search for punctuation in our given text. So the little scaffolding code is in the previous code chunk. You can formulate something similar to provide me with, or provide the get as output the punctuation. So I'll give you a minute to try this bit out, and before I move on to explaining the different linguistic features that we can get. Okay, so the most basic classification of tokens that we can do with any language model is it a word? Is it not a word? Is it a punctuation, right? So once we have this very simple classification or categorization task out of the way, let's look at some of the other things that a language model can do for us. Now, while discussing the pipeline that SpaCy provides us with, I pointed out that after tokenization, there is tagging followed by parsing. So what does tagging look like? Right now, the tagging is essentially a form of, in this case, linguistic annotations. Linguistic annotation is done by passing text through a language pipeline, and then accessing all of the tags that the language pipeline assigns to our tokens, right? And in the case of as far as the SpaCy's code is concerned, you'll see a lot of trailing underscores. The trailing underscore is used to ask for the English name of the label instead of a long string of unique numbers. And in order to demonstrate this, the first example. Did someone drop out of the meeting? Okay. So the first example here is extracting lemmas. So in this case, let's look at the example. I'm asking I'm asking my language model to go over the document and give me the some of the labels that are assigned with the identified tokens. So you'll notice that after the output for the code block under lemma, the model returns the name of the token. So if you look at the first one, the token is and the unique ID, the unique entry for THE that's saved inside the language model is also right. And we also can print the label that is associated with each of it. Now, as we go down this list, let's look at the last two entries over here. Now, if you notice for the token traditions, which is the plural of tradition, the lemma is tradition, like the plural marker has been removed. This is because ultimately, as far as meaning goes, traditions and tradition both point to the same concept, and so they're assigned the same lemma. Similarly, if we look at the next entry, focusing, the lemma is focus. Again, we've removed the morpheme for present continuous, and we're pointing directly to a meaning entry that SpaCy has stored for us, right? So what does lemmatization do? It's just a way of getting to the meaning of the different words as a initial step for doing more complex things, right? The next thing that we can do is we can access the parts of speech tags, right? And this is a grammatical type of a given token, and really good for identifying content words versus function words. And if I do the same call one more time, I'm asking for the token, the pos tag, and the pos label. So if we look at the first printout over here, for the word funny, the pos label is ADJ, which stands for adjective. If you look at the next one, movie, it's been identified as a noun. We are also able to identify our prepositions, and there are depending on the complexity of the sentence that you give, there are lots of pos labels that will be assigned to each word. Typically, this also depends on the context of the sentence. So as you know, many words can function as both nouns and verbs, and so SpaCy, the language model that you provide, is going to look at the context and then assign the pos label accordingly, right? And once we know the parts of speech tags and labels for our tokens, the next thing that we can query is syntactic dependency. Basically, this helps us build a little tree to what's called like the graphical tree, and what a syntactic dependency tells us is the relationship between different words in a sentence. So once we know what the meaning of each individual word is, once we know what role it's playing in a sentence, the next thing we want to know is what relationship do these words have with each other, so that we can correctly extract the meaning. And this is the sort of thing that will help us tell the difference between the sentence, I am a cat and I am not a cat. Both of these sentences have opposite meanings. And in order to get our model to understand the distinction between a negative being present in a sentence and not being present in a sentence, we have to make sure that we understand how the sentence has been constructed. So again, another simple print statement. In this case, in order to get the dependency, the function I'm using is .dep, and the trailing underscore is just to make sure that I get the labels, the human readable labels. And if you look at the sentence that's been printed out here, the second column in this little table will tell you the parts of speech tag for each of them. So we've got our pronouns, we've got our nouns, we've got punctuation. In this case, we've got conjunctions. All of them are here. And next, it also tells us about the dependency labels. And you'll notice that we in this list, only nouns and verbs have been listed. And there's also the head of the sentence. So these are just more labels that are assigned in order to understand the relationship between the words, right? And once we have all of the parts of our pipeline set up, we've understood which parts of our strings are tokens, what these tokens should be tagged as, what their relationship is with each other, and how they function in a sentence. The next thing would be to run a simple task in order to see how all of this comes together. So the simplest NLP task that we can run would be a named entity recognition, or NER. What this does is look through your text and look for entities which happen to have unique names. So for example, if your sentence is United States as a country, our named entity in this sentence is the United States. And we might want to extract our named entities for the purposes of our language task. And this is something that can be run very quickly and very simply with SpaCy. Oh, sorry about that. 1 second. Sorry, it looks like some of the cells were not run, but essentially, if you've been running all the cells so far, what this should do is what this print statement does is print all of the items and along with their labels in a given sentence. And in order to get to our named entity recognition task, the first thing we might want to do is make sure that we are processing our stop words and punctuations out. So stop words are are words in a sentence that aren't really carrying the meaning of the sentence. So typically, these are any words which are not nouns or verbs. And sometimes if we have a massive corpus of data and we're very specifically looking for named entities, or we're looking for meaning, we might not want all of these bloated words to add to our processing time. So a simple task that we can do before we feed billions and billions of lines of text to another big model is to simply extract and filter out all of the stop words. And in this case, since SpaCy is already assigning stop word labels to every token to the tokens that it's encountering, we can simply use those to call and extract them. So in this case, I want to extract all of the words that are not stop words and are not punctuation, and that gives me a smaller corpus. So as you can see, this is one way for us to basically remove anything that isn't really contributing to meaning. SpaCy tends to preserve articles, and this is because sometimes in the downstream, we might want to know if a definite or an indefinite article has been used, because the horror versus a horror may not carry the same meaning. So it's just a little quirk, but also very useful. Now, up until this point, there have been a lot of functions and there have been a lot of labels, and it's not possible for anyone to keep track of what each of these tags and labels mean. So something that you can do is simply ask SpaCy to explain all of the labels that it's using. The command for that is .explain. And once you run it, it tells you, it can tell you anything about the labels that it assigns, right? So up until this point, most of our discussion has been the building blocks of natural language processing. We like to label, we like to identify our tokens. We like to label them in all kinds of different ways. We like to make sure that when our system is identifying a sentence, we want to know what the relationship is between each word in a sentence. And once we have all of this information, we can use it for different tasks. So another simple task that you can carry out would be a similarity calculator. We might want to know how similar two sentences are to one another. And before we do the programmatic way, I'd like you to invite you to consider how you look at or read two sentences and understand if they're similar to each other or not. For example, if I have two sentences, this is a dog and this is a cat, and let me give you a third example. The book is good. Is there a way in which your brain is calculating the distance between these sentences? Do two of these three sentences sound more similar to each other than the third? And if that's something that you feel, what are the clues in the sentence that you're using in order to understand similarity and dissimilarity, right? And while keeping this in mind, let's look at how SpaCy does similarity calculation. Now, if you'd like to do similarity calculation, we have to go over all of the steps again. The first thing that we want to do is we have to load our language model. Once we have our language model in place, we process our text through the language model. And once we have our two documents ready, we can use it for our first NLP task, which is the similarity score. I'm asking SpaCy to tell me how similar I like horror movies and I like scary movies are to one another. So this should generate a simple in numerical, like a float value. In this case, the float value is 0.96, which is basically 96% similarity. Consider what is similar about these two sentences. I've got, the both first person sentences, the verb is the same, and I've been using synonyms for both for the named entity that we're using here. So horror movies, scary films, there's a lot of similarity in these words. And I have some more examples here. You can replace in the next code box, you can replace it with any sentence that you'd like, and try to see what similarity calculations you get for different sentences, right? And another thing to keep in mind here, if in my example, I've given a simple 4-word sentence, try seeing what happens if your two sentences have 10 words. Does it impact similarity calculations? I'll leave you to I'll give you a minute to maybe try out a few sentences. I have a boilerplate, two boilerplate sentences printed here, but please feel free to replace this with a sentence of your choice. And I invite you to try out sentences of different lengths, like try out a sentence with 13 words and see what the similarity calculation comes out as. All right. So when it comes to a task like similarity calculation, what our pipeline is doing for us is it's looking at how close or how far two words are. And the determination for this closeness or distance comes from assigning each word a vector, which is a mathematical representation of the given token. This vector depends on how often a word has been seen in the company of other words, how often has a word been seen in a certain context, and what are the other words that appear in the space, in a similar space. So it's a way of arranging our words in order to determine which words are clustering with each other, which words are more far away in terms of meaning and use. And if you'd like to actually look at the vector value for different tokens, SpaCy does allow you to print those. In this case, the way to do it would be to call the dot vector value for a given entry. So if you do phrase dot vector, and phrase is your variable in which you've saved a bunch of things, it will print out the vector value. And once you run this code block, you'll see that the vector is essentially a long string of numbers that are listed together. And each word has a different vector representation, which depending on how close or how far the vector representations are, that is the information that's being used for similarity calculation. Now, this is being done in a very small in a very small and controlled manner. But if you think about a large language model, it's a very similar process that's happening at a much larger scale, along with a lot more other calculations. Okay, so another thing that we can do is if we have, since we have all of our entries and they all have tags, we can search for the lemmas by their pos tags. So in this case, if I want to look inside my vocabulary and I'm interested in understanding more about a particular word, I can look for its entry inside the language model's vocabulary, and I can do this search by not just using the word itself, but by using some of the tags that have been assigned to it. So in this example, I have, as always, I process my text through my language model in order to create my document. And I'm using just a simple print statement in order to print out the values that are assigned to the different pos tags, right? So in this case, you'll notice that when I run this print statement, it returns a set of tuples, and in each of them, we've got the determiner, we've got the pos tag that's printed along with the word itself. And why is this useful? If you're interested in looking into a document and you want to search a document and you're only interested in finding out what kind of verbs have been used, this is one way to do it. Now, as you might know, sentiment analysis, one of the things that it's looking for is keywords that express some kind of positivity, negativity, emotion. And many of these words predictably tend to have the same pos tag, right? So if you're interested in analyzing a piece of text, and we know that most of the sentiment tends to live in, say, the adjective tags, or it lives in the adverb tags, it might be useful to simply look through your document as a preliminary step and just extract all the adjectives and see what kind of words are being used, right? And so before we embark on a larger task and use billions of lines of text, we might want to start very easy and look through our document and do a little bit of pos matching, right? And in this case, we can also look through our document and see if two sentences are similar to each other or not. So in this case, in this example, I have two sentences, that love is obsessive and you love me. Now, in both of these sentences, the word love appears, right? But they're not actually, they're not carrying the same meaning. In the first case, the parts of speech tag associated with love is noun, And in the second case, it's verb. And so we can use this information in order to match, in order to effectively match our our text documents in order to make sure that our sentences can be correctly disambiguated, right? So in case you're running a task where you really don't want to have your model confused between words that tend to have the same alphabet, the same characters in them, but tend to have but have completely different say meaning, using the pause tag would be one way to do it. Right. Now, having looked at all of the parts, all of the pieces that make up our language pipeline, so far, all of the tasks that we've looked at, they've all been, I would say, jigsaw puzzles. And now that we have all of our pieces in place, let's consider one way to bring all of this together with just a very simple NLP task, and something that can help us run everything end to end. And in this case, I think I invite you to imagine that you have a massive data set in which you have lots of film reviews, you have lots of text. And before you decide to use all of this and exhaust your compute hours, you might want to do some basic text in data investigation. And so what is a way in which you can use a NLP tool like SpaCy in order to investigate or just look at your data, or just understand your data better before you plan a more complex downstream task, right? So today we're going to look at a movie review data set. I've taken this from Kaggle, which is a great place for finding both tasks as well as data. And after loading the 50,000 movie review data set, for the processes of my analysis today, I'm just going to create a random subset of 1,000 movie reviews and see what I can do with them, right? So for the data management, I'm going to use pandas. I have saved this little subset of the data in the GitHub repository. And so when you run this, when you run pandas, it will show you a data frame. And if you look at the column names, we've got a review and sentiment. So in this case, review contains a long description of the given of what someone thought of a movie, and the sentiment contains positive or negative, so two kinds of labels. All right. And if you'd like to just explore and just look at the data, this is just a sample of what it looks like. We've got the review has all of our interesting text. The sentiment is just two words. And something that the next thing for us to consider is where does our sentiment analysis information exist? So our data set is providing us with annotations, but if we want to use or get something meaningful done with this data set, we might want to actually look at the text itself. So we know that the column review is where all of our all of the linguistic data lives. So I'm just going to look at it specifically. And I'm going to, in order to look for this, to look into this a little bit, I'm going to, for the next step, I'm just going to look at 500 reviews in our data set. And now that I have them, the first thing in order to run an NLP task, I don't really, especially something like sentiment analysis, I probably don't need all the stop words in the sentence. I probably don't need the ands and the buts inside the sentence. I probably don't need the conjunctions. I might not need a lot of the prepositions. So the first thing I'm going to do is I'm going to basically remove the stop words, which is happening here. Right, it's just all I'm doing is identify the stop words and set them aside is what I'm telling the model to do. Just one second. All right, so this step will take a little bit of time because it is going to read through your text and something again worth considering, that whenever we are working with language models, and we don't and we are looking at compute, all of these steps do take a certain amount of whether we see it or not, there's a certain amount of computational time involved, and using our NLP tools is something that helps us ensure that we're using all of our resources in an efficient manner. Right now, if my simple NLP task, something that I'm thinking of, I want to find out or look for a few movies that I want to watch with my friends, right? And in order to do this, as many of you might do, if we're using our browser and we're just not doing this programmatically, we might just go to IMDb and just read the reviews for different movies, look at their ratings, and try to pick a movie, right? And in order to pick our movie, we might also want to choose a genre, right? So if I want to watch a horror movie with my friends, first up, I might want to look inside my data set and identify movies that are happen to be belong to the horror genre. I might also want to make sure that I'm watching a good movie, and so I might this is an example. I might decide to use the sentiment label inside our movie. So once I've identified whether a movie happens to have appeal to the public or not, and I've been able to identify movies that fall into the category of movies that I'm interested in watching, I can look and assess how many people or how many people thought that horror movies in a given data set were interesting or not. So once I downsample all of my movie reviews to extract only the positive movies, the movies with the where the reviews were positive, the next thing I want to do is create a little phrase matcher in order to look for words that might be useful for identifying a horror movie. So I've made a little list over here, but feel free to add to it or subtract to it. I mean, if you have a different phrase list, I mean, if you're interested in searching for a romantic comedy or for a thriller or for a movie in the crime genre, you might want to change your phrase list to use completely different words, right? So if you're following along and you're interested in testing the pipeline out, feel free to change the phrase list and see what happens. I'll just give you a minute to consider the phrases. For if you're considering looking at horror tokens, then think of any other words that you would encounter or you would use to describe a horror movie. Right. So once we have our phrases, we can use the SpaCy's phrase matcher function or class in order to identify in order to match the phrases that we are looking for within our corpus of text, right? So in this case, once I have all of my words, the next thing I'm doing is I'm going over my text and building my phrase matcher. And once I have my phrase matcher ready, I have my data set ready, the last thing to do is simply run my phrase matcher through my data set and find the movies that could be possibly belong to the genre that I am looking for. Right. So if you run our final data step over here, you'll notice that the print statement will return all of the sentences in which the phrases that we were looking for were available in the text, right? And so the next step is to actually evaluate our corpus. Now, remember, we only looked into 500 of the data of the reviews. We actually have 50K reviews to go over. And this small step, this initial step gives us a sense of what the task is like, how complex is the task, how much time will it take, how much resources will it take, and what are the ways in which we can make things more how we can optimize the task, right? So once if you've followed along to the last step, you'll notice that there's a bunch of movies here. Now, in this case, the last step over here is to evaluate if the phrases that we provided were actually useful to identify horror movies, right? So at this point, I invite you to look at the output, see if the output was actually relevant or not. And if not, if it wasn't relevant, what are the improvement steps that we can do in order to ensure that our NLP task is properly set up, right? So the example I've given here is definitely a toy example. It's a very small step in how we can set up bigger tasks. Now, the main thing that I'd like to leave you all with is just a sense of how an entire pipeline end to end would work. And if you are interested in an NLP task, what are some of the ways in which you can explore or do some data exploration with the corpora or data sets that you might have, and what your initial sense would tell you. So this is by no means how a real world example would work, but it's just a simple way for us to put together all of the steps and all of the tools that we looked at today. And further, I have just some questions for you, open questions. You can choose to answer them, or you can choose to think about it a little bit more. First is, of course, the quality of the output. If we are simplifying our NLP task down to just identifying phrases, what did the quality of output look like? Were we able to identify the horror movies correctly by doing phrase matching, right? Next thing is, we've looked at a whole bunch of other tools that SpaCy provides us. So in order to improve the efficiency of this task, are there any other NLP tools that we can use in order to improve how we go about things? All right, so these are open questions, and in case you have any questions about the tools that we have today, let me know in chat, or you can reach out through the Data Lab email ID that we will add in the chat in a minute. And last and certainly not the least is all of the SpaCy resources. I covered some of the tools that were relevant for some of the examples I needed for today's demo, but SpaCy does have a fantastic documentation. It has support for other languages. So I had to today I gave examples with English just as a language that we all might share. But if there is any task that you're running on languages that are not English, there are resources for it. I've used SpaCy's Spanish language models, and they work pretty great. There's also non-European languages that are available to you. So that is all I have for you today. If you have any questions, I'll be around till 1. And if not, thank you so much for joining me. Thank you for, I hope that you return for our session next week, where we will look at using regular expressions as part of natural language processing. And our future sessions are listed in the repository, and if any of the other they're not really linked to each other, so it's if there's a different session that's more relevant to you, please feel free to join me. Right, thank you so much.